Having discussed the DeepLIFT method and the performance on MNIST data, we now discuss the results on simulated genomic data. Let's talk about how we create our simulated data. The basic idea is that we will first generate a random background sequence and then embed patterns within this sequence that correspond to our different prediction tasks. For our patterns, we will rely on position weight matrices, that's PWMs, which describe the probability of observing a particular letter at a particular position. For instance, this is the tal1_known1 PWM from the ENCODE database, which is a PWM that was found to characterize the binding sites of the tal1 protein. The specifics of our simulation parameters are as follows. For our background sequence, we will sample an A or a T with 60% probability, and will sample a G or a C with 40% probability. In genomics terminology, we will generate a sequence with 40% GC content. Into this background sequence, we will insert 0 to 3 motif instances sampled from the GATA_disk1 PWM and 0 to 3 motif instances sampled from the tal1_known1 PWM, which were obtained from the ENCODE consortium. Our outputs consist of 3 binary classification tasks. Task 0 is 1 for sequences that contain both a tal and a GATA motif embedded. Task 1 is 1 for sequences that contain a GATA motif, and task 2 is 1 for sequences that contain a tal motif. A quarter of the sequences we generate have both a tal and a GATA motif embedded and are labeled 1, 1, 1. A quarter have only a GATA motif embedded and are labeled 0, 1, 0. A quarter have only a tal motif embedded and are labeled 0, 0, 1. And a quarter have neither embedded and are labeled 0, 0, 0. Note that sequences that resemble a motif can occur by chance even if we have not embedded them. And for more details on the simulations, please see the appendix. Now that we covered the setup of the simulations, let's evaluate the performance of different importance scoring methods. In order to do that, we must first identify the characteristics that our ideal importance scoring method would have. Let's consider scores on instances of a tal motif. For task 0, which is 1 for sequences where both tal and GATA motifs are present, we want high scores on strong matches to a tal motif. However, more specifically, we want higher scores on the tal motif if the sequence also contains a GATA motif than if the sequence only contains tal motifs. This is another way of saying that we want our importance scoring method to detect cooperativity between tal and GATA. That is, tal is more relevant for task 0 if there is also a GATA present in the sequence. For task 1, which is 1 for sequences where a GATA motif has been embedded, we want scores near 0 on instances of a tal motif. This is because a sequence is no more likely to contain a GATA motif if we know that a tal motif has already been embedded in it. For task 2, which is 1 for sequences where a tal motif is embedded, we simply want high scores on strong matches to the tal motif. And of course, we expect to see the analogous trend for the GATA motif, high scores on task 1 and near 0 scores for task 2. Now that we have identified the characteristics of our ideal method, how can we do the assessment? We first trained a model that had 2 convolutional layers, a global average pooling layer and 1 fully connected layer that attained over 0.98 AURC on all 3 tasks. On each sequence, we identified the top 5 matches to a given motif as sorted by the log odd score that a particular match originated from a particular PWM versus the background base frequencies. Then, we sum the importance score assigned to each match by different methods for a particular task, and plot the importance score against the strength of the log odd score. For DeepLIFT and integrated gradients, we use a reference input representing the frequencies of ACGT in the background set. However, we also explored using multiple different references per sequence, where the references were obtained by shuffling each original sequence. That is, for each sequence, we generate several references by shuffling the sequence and average the DeepLIFT results obtained over the different references. Those results are given in the appendix, and in the simulation, both approaches to defining the reference give qualitatively similar results. But why might we prefer to use shuffled sequences as a reference over the frequencies of ACGT? Well, one danger of using an artificial reference, such as the frequencies of ACGT, is that the net never sees such an input during training and can sometimes give very unexpected predictions on it. In practice, if you want to use a fixed reference like the ACGT frequencies, you should double-check the kinds of outputs that the net gives when supplied this reference input. For example, if the net very confidently predicts that the background frequencies of ACGT is a member of a certain class, then unless you're okay with that class being your reference output, you may want to opt for a different way of picking the references. Here are the results shown for task 0 and the tal motif. On the x-axis is the strength of the log odds score for the match to the tal motif, and on the y-axis is the total score assigned to the match. Red dots are from sequences that contain both a GATA and a tal motif, and green dots are from sequences that contain only a tal motif. Integrated gradients -5 means the numerical integration was done over 5 intervals, and integrated gradients -10 means the integral was done over 10 intervals. DeepLIFT-rescale uses the rescale rule of DeepLIFT at all nonlinearities. DeepLIFT-reveal cancel uses the reveal cancel rule at all nonlinearities, and DeepLIFT FCRC conv-RS uses the reveal cancel rule on the fully connected layer and the rescale rule on the convolutional layers. You can see that the red dots tend to lie above the green dots, consistent with the tal motif being more important if it occurs in the presence of a GATA motif. However, note that for gradient times input, integrated gradients, and DeepLIFT with the rescale rule, some red dots with a high log odds score end up with important scores below 0. These are false negatives, if you will. One hypothesis for why this occurs is that modeling cooperativity between tal and GATA motifs requires learning an and-like relationship, which we illustrated before is one of the failure modes of these methods. The proportion of red dots with log odds score over 7 that have important scores of less than 0 are illustrated in this bar plot. You'll notice that all methods except guided backprop and DeepLIFT with the reveal cancel rule have false negatives. However, one reason not to prefer guided backprop is that it shows a tendency for false positives. For example, if we visualize the scores on the tal motif for task 1, which is the contains GATA task, we find that guided backprop places considerable positive importance on the tal motifs even though they aren't relevant for the task, while the other methods produce scores that are, for the most part, centered around 0. This is not an unexpected result if we consider that guided backprop discards negative gradients during backpropagation, thereby making itself susceptible to false positives. Now, you may notice that the scores for task 0 seem to be tiered. This turns out to be caused by having different numbers of tal motifs in the sequence. That is, the total importance for tal ends up being distributed across all the different instances of the tal motifs. For more details, please see the appendix. Finally, let's consider the scores of the tal motif on task 2, which is the contains tal task. As you can see, all the methods tend to give higher scores to stronger matches to the tal motif, which is the desired behavior. However, note that both guided backprop and gradient times input tend to have a sudden jump at around a log odds of 7, with a more gradual increase thereafter. Compare this with the behavior of gradient times input for thresholded functions. We have a sudden jump at around the threshold and then a more gradual increase. The practical consequence of this is that weak matches to the motif can receive undue importance, as we will see on the next slide. This is also the reason for why the scale on the y-axis is so much larger for gradient times input. A lot of compensating negative importance is placed on the bias terms. Here is the behavior of the different methods for task 0 on an example sequence that contains both an embedded GATA motif and an embedded tal motif. The height of the letters is proportional to the importance score on the letter. The blue box indicates the location of an embedded GATA motif, and the green box is the location of an embedded tal motif. As you can see, the DeepLIFT methods that use the reveal cancel rule are the only ones that assign positive importance to both the GATA and the tal motifs. What's more, DeepLIFT with the rescale rule applied to the convolutional layers and the reveal cancel rule applied to just the fully connected layer appears to reduce noise relative to using the reveal cancel rule at all layers. As a possible explanation for why, imagine that a particular convolutional filter acts as a motif detector with a reference activation of 0. When this filter sees a poor match to the motif, that is, some letters resemble the motif and others don't, it won't activate, and the rescale rule will not propagate importance through it because the difference from reference is 0. However, the reveal cancel rule can assign positive importance to those letters that resemble the desired pattern and negative importance to those letters that didn't, which can end up highlighting noise if the poor matches to the pattern are only due to chance. Now, Turning our attention to the rest of the sequence, the red underline shown is an accidental false positive match to the tal motif. Instead of CAG-ATG, it is CAG-TTG. That is, the second A is replaced by a T. Consistent with the results on the previous slide, we see that that gradient times input assigns a lot of importance to this match, while the other methods are a lot less enthusiastic about it. So that concludes this video series. Thank you for watching. To summarize, DeepLIFT is an efficient backpropagation-based approach for defining importance scores that leverages differences in the activations of neurons from their reference activations. Because of this, it can propagate importance even when the gradient is zero, which could prove especially useful for RNNs where gating neurons will often saturate and thus have gradients near zero. DeepLIFT can also avoid discontinuous jumps in importance that are caused due to thresholds from bias terms, in contrast to using the gradients. And finally, the reveal-cancel rule of DeepLIFT can pick out dependencies such as those illustrated with the min/and example, and it does this by giving separate treatment to positive and negative contributions. As for some open questions, by far the most important step in DeepLIFT is getting an informative reference, and it's not always obvious how to choose a good reference. Ideally, the choice of reference could be determined empirically from the dataset itself, and we have seen that empirical approaches such as shuffling sequences do show good promise. Another open question is the best way to handle max operations. Right now, if we use DeepLIFT on a network that has a max pooling layer, we just use the gradients at the max pooling layer as the multipliers. But as was shown in the paper by Lundberg and Lee, titled An Unexpected Unity Among Methods for Interpreting Model Predictions, this isn't always a great approximation to the Shapley values, so there could be room for improvement there. Finally, we are interested in exploring the applications of these methods to RNNs. We've already made a bit of headway on these questions with promising initial results, so please do reach out to us if this is also of interest to you.